Welcome to our channel, where we bring you the most interesting and informative content from around the world. Black holes. These enigmatic entities have long captured the human imagination. Just the name evokes a sense of mystery and dread, a cosmic enigma that seems to defy the very laws of nature. They are the cosmic monsters of Einstein's imagination, regions of spacetime where gravity is so strong that nothing, not even light, can escape. These regions are defined by their event horizons, the point of no return. For decades, these enigmatic objects have captivated scientists and the public alike, inspiring countless works of science fiction and fueling our fascination with the unknown. From the pages of novels to the screens of Hollywood, black holes have become a symbol of the ultimate frontier. But what exactly are black holes? How do they form, and what role do they play in the grand tapestry of the cosmos? What would happen if you were to fall into one? Would you be stretched into a thin strand of atoms, or would you find yourself in another universe entirely? The answers, as we'll discover, are stranger than fiction. They challenge our understanding of the universe and force us to confront the limits of physics as we know it. Black holes are not just theoretical constructs, they are real, observable phenomena. They challenge our understanding of the universe and force us to confront the limits of physics as we know it. They are the ultimate test of our scientific theories. Join me on a journey to the edge of reality, as we explore the science behind these celestial behemoths. We'll delve into the bizarre effects of extreme gravity, from time dilation to spaghettification, and contemplate the ultimate fate of everything that ventures too close to a black hole's gaping maw. We'll delve into the bizarre effects of extreme gravity, from time dilation to spaghettification, and contemplate the ultimate fate of everything that ventures too close to a black hole's gaping maw. Time itself behaves differently near a black hole, slowing down to a crawl as you approach the event horizon. Spaghettification, the process by which objects are stretched and torn apart by gravitational forces, is one of the most mind-bending consequences of black holes. Imagine being stretched into a long, thin strand, like a piece of spaghetti, as you fall into the abyss. Our exploration will take us from the familiar realm of stars and planets to the very heart of a black hole, where the laws of physics break down and the universe reveals its most profound secrets. At the singularity, the core of the black hole, the known laws of physics cease to apply, and we are left with more questions than answers. Where the laws of physics break down and the universe reveals its most profound secrets. What lies beyond the event horizon? Is it a gateway to another universe, or a dead end where all information is lost? These are the questions that drive our quest for knowledge and understanding. To understand black holes, we must first understand gravity. Gravity is one of the fundamental forces of nature, and it governs the motion of planets, stars, and galaxies. It is the force that keeps us grounded on Earth and dictates the orbits of celestial bodies. Gravity, as Einstein taught us, is not a force but the curvature of spacetime caused by mass and energy. This revolutionary idea was part of his general theory of relativity, which fundamentally changed our understanding of the universe. Imagine a bowling ball placed on a trampoline. The ball creates a dip, and any object rolling nearby will curve inward towards it. This simple analogy helps us visualize how massive objects like stars and planets warp the fabric of spacetime. Similarly, massive objects in space warp the fabric of spacetime around them, influencing the motion of nearby objects. This warping effect is what we perceive as gravity, and it affects everything from the path of light to the trajectory of planets. Black holes are the ultimate expression of gravity's power. They are regions in space where gravity is so strong that nothing, not even light, can escape their pull. This makes them some of the most mysterious and fascinating objects in the universe. They form when massive stars collapse at the end of their lives, compressing their immense mass into an infinitely small point called a singularity. This collapse is so powerful that it overcomes all other forces, leading to the creation of a black hole. This singularity is thought to be at the very center of a black hole, a point of infinite density and zero volume where the known laws of physics cease to apply. The singularity is shrouded in mystery, as our current understanding of physics cannot describe what happens at this point. Surrounding the singularity is the event horizon, the defining feature of a black hole. The event horizon is not a physical surface but rather a boundary in spacetime. The event horizon is the point of no return, a boundary in spacetime beyond which gravity is so strong that nothing can escape, not even light. Once an object crosses this boundary, it is inevitably drawn towards the singularity. It's important to note that black holes are not cosmic vacuum cleaners. They do not roam the universe, sucking in everything in their path. They don't suck in everything around them. In fact, if our Sun were replaced by a black hole of the same mass, the orbits of the planets in our solar system would remain largely unchanged. Only if you cross the event horizon are you doomed to be consumed. This boundary marks the limit beyond which escape is impossible, making black holes both fascinating and formidable objects in our universe. Imagine you're an intrepid space traveler, venturing closer and closer to a black hole. From a distance, it might appear as a dark void against the backdrop of stars. However, as you approach the event horizon, things start to get weird. One of the first things you'd notice is the distortion of light. Gravity bends the path of light rays, and near a black hole, this bending becomes extreme. Stars behind the black hole would appear to be in different positions than expected, their light warped and magnified by the intense gravity. As you cross the event horizon, you wouldn't feel a bump or a sudden jolt. From your perspective, you'd continue inward, only now there's no turning back. You're trapped. The immense gravity of the black hole now prevents you from sending any signals back out, including light itself. Section 4, A View from Afar, Time Dilation and the Outside Observer. Now, let's imagine what your journey would look like to someone observing from a safe distance. This observer could be a friend, a scientist, or even an automated probe, positioned far enough away to avoid the intense gravitational effects of the black hole. As you approach the event horizon, they would witness something truly bizarre, time dilation. This phenomenon is not just a theoretical concept but a real effect that has been observed in various experiments and astronomical observations. Time dilation is a consequence of Einstein's theory of relativity. According to this groundbreaking theory, the fabric of space and time is interconnected and can be warped by massive objects like black holes. It states that time is not absolute but is relative to the observer's frame of reference. This means that two observers, one near a massive object and one far away, will experience the passage of time differently. In simpler terms, gravity affects the flow of time. The stronger the gravitational field, the slower time runs. This effect has been confirmed by experiments using highly accurate atomic clocks placed at different altitudes on Earth. The stronger the gravitational field, the slower time runs. This is why time passes more slowly on the surface of the Earth compared to a satellite orbiting high above. As you fall towards the black hole, your friend watching from afar would see your clock slow down. This isn't just a minor slowdown, it's a dramatic deceleration that becomes more pronounced as you get closer to the event horizon. From their perspective, you would appear to move slower and slower as you get closer to the event horizon, eventually appearing to freeze in time at the very edge. This is because the light signals from you take longer and longer to reach the distant observer. They would never actually see you cross the event horizon. Instead, your image would become increasingly redshifted. Redshift is a phenomenon where the wavelength of light stretches, making it appear redder. Your image would simply redshift, becoming fainter and redder as your light struggles to escape the black hole's gravitational pull. This redshift occurs because the gravitational field is so strong that it stretches the light waves, making them lose energy. To them, you would be forever frozen at the point of no return. This is a haunting and fascinating aspect of black holes, where the laws of physics as we know them seem to break down. The event horizon is often referred to as the point of no return, because once something crosses it, not even light can escape. This makes black holes some of the most mysterious and intriguing objects in the universe. Understanding time dilation and the perspective of an outside observer helps us grasp the mind-bending nature of black holes. It challenges our perceptions of time and space, pushing the boundaries of our knowledge. As we continue to explore the cosmos, phenomena like time dilation remind us of the incredible complexity and beauty of the universe. They inspire us to keep questioning, keep exploring, and keep pushing the limits of what we know. Section 5, Spaghettification, stretching towards oblivion. But let's get back to your experience as you fall into the black hole. As you venture deeper into the black hole's gravitational grip, you'd encounter another bizarre phenomenon, spaghettification. Spaghettification is a consequence of the extreme tidal forces present near a black hole. Tidal forces arise because the strength of gravity decreases with distance. This means that the gravity pulling on your feet would be significantly stronger than the gravity pulling on your head. As you fall towards the singularity, the difference in gravitational pull between your head and your feet would become more and more extreme. You would be stretched out like spaghetti, becoming longer and thinner as you descend. The process of spaghettification would be incredibly violent, tearing apart not just your body but also the very atoms that make up your being. You would be stretched and compressed until you are nothing but a stream of subatomic particles spiraling towards the singularity. Section 6, Beyond the Veil, Speculations on the Singularity. What lies at the very center of a black hole, at the singularity? This is one of the biggest mysteries in modern physics. Our current understanding of physics breaks down at the singularity, so we can only speculate about what might be found there. Some theories suggest that the singularity is a point of infinite density in zero volume, a place where matter is crushed beyond recognition. Others propose that quantum effects might prevent the singularity from becoming infinitely dense, perhaps leading to a quantum bounce or a gateway to another universe. However, it's important to remember that these are just speculations. We have no way of directly observing the singularity, as no information can escape from beyond the event horizon. The true nature of the singularity remains one of the most profound enigmas in the cosmos. Thanks for watching. Don't forget to subscribe, like, comment and share.